In order to illustrate some of these ideas of the formal definition of a limit, let's take exercise number 8 from the textbook, where they present a particular limit that we are given, the limit as x approaches 0 of e to the 2x minus 1 divided by x, which we are told equals 2. We're not asked to evaluate this. The tools for doing this analytically will come later. This is a more challenging limit than what we've dealt with so far. But if you were to use numerical or graphical methods, you would come to believe that this limit is 2. So let's use that idea to kind of illustrate the kinds of things we've been doing, or the kinds of things we're talking about in this section. So let me start by just sort of sketching a very crude graph of what this thing looks like. You will probably, it's not strictly necessary to use a graphing calculator for this, but that will be the easiest way to do this. We'll need to solve a few equations, and those equations will not be approachable analytically. Numerical solutions will be our best hope here. So of course, one of the first things you want to do is take this function as the first function that you graph, right? So you would want to put in, in a typical like TI style y equals screen, you would have something like y equals, don't forget parentheses where they are necessary. So you'll need to, group your numerator and also your exponent. So you'll put something like that in, or the equivalent in whatever other graphing utility you're using. And once you graph that, let me just kind of give ourselves a rough scale here. That's about 2. Let's put 3 around there. And you'll get something that looks kind of approximately like an exponential function. I'm not drawing this very well. It kind of depends on where you put your x values also. I think I stretched this out a little bit, so that's probably about -1. Actually, you know what? I don't want to mark an x scale because I don't remember exactly where that goes. But you'll see some curve coming up that appears to cross around 2. So even though we can see that this is undefined when x equals 0, the graph suggests that it goes that it gets pretty close to 2. So let's talk about what that means to have something that is close to 2. We're asked for this limit to find values of delta that correspond to epsilon equals 0.5 and epsilon equals 0.1. Those are 2 separate but related problems. So let's first turn our attention just to epsilon equals 0.5. So that's the one we'll focus on first. Remember, we think of this epsilon as standing for error. So we imagine that there's an error tolerance of 0.5. The limit is claiming that the function is getting close to the value 2, but in this first part, we're allowing for an error of plus or minus 0.5. So that's basically, we have 2 plus or minus 0.5. In other words, the limit L plus or minus epsilon. Okay. Now, like I said, we'll have to solve some equations here, but the easiest way to do that in a case like this is graphically. So if you go back into your y equals screen, you can graph 2 more functions. And those are the constant functions corresponding to the bounds on this. If we subtract 0.5 from 2, we get 1.5. And if we add our epsilon value, we get 2.5, right? So if you put those in as additional functions and graph those, this is clearly not quite to scale. These should be at 1.5 and 2.5. Use your imagination. You get something like this. And you'll see, of course, that this will there will be 2 points of intersection here. We're asked to find values of delta that correspond to that value of epsilon. So what they're asking us for here, the delta means the difference or the deviation, the distance that we can stray from the x value that we're approaching. In this case, 0, right? So in this context, a equals 0 in the language of the limit definition. So this is our f of x, e to the 2x minus 1 over x. A equals 0, L equals 2, and we're asked to do a couple of things with epsilon being 0.5. So what we need to do is find out, here's 0. This is asking us how far away from 0 can we go, how large a radius, how much variation can we have in x, and still keep all of the function values within 0.5 of 2. Keep all of our function values within this error bound here, this neighborhood that we have centered on 2. Okay. Here's 2. We're going 2 plus epsilon and 2 minus epsilon. So we have this kind of band here, this neighborhood. We want to keep everything inside of that. Well, to do that, we will want to know the x values of those intersections. Okay. And finding that, you will want to probably use your graphing utility's intersect or intersection feature that allows you to place these things. It'll probably ask you which curves you want, so you'll have to arrow through to make sure you're choosing the right curves. And some utilities will ask you for an upper and lower bound, some of them asking you for a guess. Check your appropriate manuals or references, or ask me questions if you're not sure how things go. But if you look for the intersection points here, on this one, for y2, it's 1.5. So this would be your y1. This would be what I put in as y2, and this is what I put in as y3. So the intersection point here, we find that our x intersects at approximately, where is this? Negative 0.30293. And this intersection here occurs at approximately 0.21542. Now, I haven't recorded these to a lot of accuracy. A particular problem would probably specify how many digits of accuracy they need if it's in WebAssign, for instance. For our sake, let's just suppose that we're looking for 4 digits past the decimal place. 1 part in 10,000, that should be good enough. So each of these suggests a different delta value. We have, that was a weird looking delta. Let's try that again. That's even worse. I'm not sure if I've drawn a delta on my tablet yet. That's not great, but it'll have to do. So we have a delta 1 that we have here. If we round this to 4 places, now delta is supposed to be the difference, so we're not concerned about whether this is positive or negative. So we would just take the 0.3029. Now there are a couple of things to remark about here. One is that this particular problem is a little bit easier to interpret because our a is 0. We're looking at how far above and below 0 we go. So the x values we find, if you just strip away the negative, that's the delta. That's how far away it is, right? Another problem, if you have an a that is a non-zero value, then you will need to subtract to find the difference between a and x, right? So, if we were looking at something, maybe we were actually looking at a limit of like -1, for instance, and we got this x value of -0.3 whatever, well, then we would have to find the actual difference between those. It's how far away from a, and, you'd subtract and get something a little under 0.7 or whatever, right? So it's that difference that we're looking at here. But in this case, thankfully that's just around 0, so it's a little bit cleaner. We have this delta here. Now, the second thing that I want to point out is that I specifically rounded down, not because this was a 3, and 3 is closer to 0 than to 10, but because we're trying to find values of delta that will guarantee that any x not exceeding that delta would produce a function value that is within epsilon of the function in question. Okay? If you take a difference and you round it up, even because it's really close to the next thing up, then that could potentially scoot you just a little bit outside of that neighborhood. And now you could have x values where when you evaluate the function there, it's not within epsilon of the thing you were asking about, and that's not what we want. So when doing these computations, you want to round the delta in towards, basically you round your delta down towards 0. I hope WebAssign accepts such answers. If it doesn't, you might need to just round them to the nearest as you're accustomed to. But keep in mind in the back of your head that for actual error bounding and tolerance work in more precise analysis, you'll want to make sure to err on the side of caution, to take a conservative estimate and round towards 0, so that you keep that little bit of buffer and don't accidentally allow things to spill out. Anyway, so this is the first value of delta that is suggested. The second one, again, I wanted to take these to 4 decimal places. So I'll round that down to there. Sure, the 2 is closer to the 4, but again, even if this were like an 8 or a 9 or something, I would still round that down and leave that a 4 because we don't want to risk spilling over. But something to be clear about here is that when we talk about a delta corresponding to an epsilon, we only want one of them. Okay? Now this says values plural, but this is values of delta corresponding to this value of epsilon and that value of epsilon. In other words, this problem is asking us for 2 values of delta. There's one value of delta for epsilon equals 0.5, and a second value of delta for epsilon equals 0.1. So we only want one delta for this, and we have 2 options depending on which way we're going. But remember from our definition, we're talking about a bound here, right? We want the distance between x and a to be less than delta, which if you interpret as, if you interpret that on a number line, and you have a value a, that means that you're going to go some distance of delta, sort of a radius of delta to the left and right. Okay? A minus delta, a plus delta, same distance. It's like the center of a circle, except it's in one dimension. So we want to choose a particular delta. Now these 2 values that I found are the distances to the left end of this range. Basically, I should mention that the numbers that I found here, from here to here, any x values between these, except at 0, if we evaluate the function at any of those, we get a function value that is between the bounds we had based on epsilon, between 1.5 and 2.5. Right? Everything fits within this box right here. Down in this neighborhood, we call it formally. Or informally. I'm not sure if that's technical or not. Now, if we choose... So we have one at about 0.3 and one at about 0.2. If we were to choose the one that was about 0.3, we'd be going about 0.3 to the left, which is fine, but also 0.3 to the right, which is not fine. That would spill outside of that. So once we know the distances to the 2 ends of that interval, we need to choose the one that is closest as our radius. So the smaller of these, the actual value of delta we want, is the minimum of the 2 values that I found, delta 1, delta 2. And that, in this case, is approximately 0.2154. Okay. So from this little bit of numerical work we've done, a little bit of conservative rounding, we are quite confident, assuming that our calculator isn't lying to us too much, we are quite confident that as long as we choose x values that do not exceed a distance of 0.2154 from the origin, any function value we get when we evaluate our function at that point, it should give us a value that is within 0.5 of 2. Okay. Now, that was the first part of this problem. Second part asked us about 0.1. Well, I'm not going to work through all of that. The details are much the same. I'll leave that to you to try out and confirm. This was an epsilon boundary of 0.5 above and below. 0.1 would be something much tighter, right? We would get a much narrower band here, and we would expect, when we find those intersections, we would expect to find something that is much smaller. We would expect to need a smaller value of delta, a much smaller amount of variation in x values, differences or distances or deviations, whatever you want to call it, whatever D word you want to use there, in order to fit within that error bound of 0.1. That's much tighter. So you would do something similar, except that you would edit your y2 to be something like 1.9, and y3 should be something like 2.1. And that'll give you those narrower bounds. You can find the intersections again, work with your delta values, and I'll go ahead and mention kind of the answer so you can check your work and confirm that you have done all of this correctly. When I did this, at least I got delta equals 0.0483. So again, this was for the this was all for epsilon equals 0.1. So you can try that using the same technique. Make sure that you can get that to work out. And keep that in mind. I know that the first time you see the formal definition of a limit, it's a little bit intimidating, and that is entirely understandable. It is logically complex. There's what is there? A universal quantifier, an existential quantifier, a biconditional, and a conditional. So in terms of just the logic, that's a complex structure. If any of you studied formal logic, you know what I'm talking about there. So it's okay to have difficulty wrapping your head around what it means initially, but hopefully playing around with some graphs like this and some numerical work can start to get you the idea of what that is, what ideas those are trying to talk about, right? And this is kind of what we mean when we talk about this being formal. This epsilon and delta handle those questions we had about, when we talk about things being close enough. What does that mean to get close to this, to approach this, as this gets close to that? Like, those are really fuzzy and wishy-washy terms, but if we needed to, very frequently in mathematics, we just continue to use those hand-wavy terms. But the point is that if we needed to, we could sit down and say, okay, what do I mean by approaching this or close enough? Well, for this particular application, an error tolerance of, 0.001 would guarantee such and such. So then, what amount of variation can we have in this you can sit down and make all of this rigorous. And all of these limits that we've been talking about, with the limit laws and what approaches what, it is all this idea of no matter how tiny you make epsilon. These are very large as far as epsilon values are concerned. But this works with much, much smaller numbers. You can take any tiny value of epsilon, as long as it is greater than 0. And no matter how small that is, you can find some tiny little sliver of a delta within which all of the x values will produce function values that fit within your error tolerance specified by epsilon. So that's what this is saying with the limit. That's kind of it's a very powerful statement, and a very precise statement in the context of this definition. So hopefully that clears up a few things, or at least gives you enough of an idea of how to approach some of these problems.